So this meeting will be also relatively brief, and next week, after some adjusting of the schedule, we'll try to dedicate a little bit more time. You still have the class at 1, right? So you need to leave 10 minutes before 1.
Oh, about 5. It's just across the road.
So you'll have like 25 minutes left. And the rest of the class, probably 2, in order to have you on the even side. So, Levi will start laughing. Who we are and what we are doing here. So we do have the Quantum Chemistry 2 course, and last time I was distributing the tentative syllabus. I can send it to everyone once again. So this is not as straightforward logical class as computational chemistry, and not as straightforward and simple class as Quantum 1. There everything was in a very interconnected linear logic. Right now we are covering the miscellaneous, the missed parts of the quantum chemistry that were not able to fit into the original course. So they are small chapters, they are not immediately connected to each other, and it will be like blocks, a couple of blocks. So first block that we are covering will be related to angular momentum. Second and third will be time-dependent and time-independent perturbation theory, and then if we have time, there will be density metrics and scattering theory. So the first block on the angular momentum is counterintuitive to regular life, but it has benefits in the quantum theory for those who deal with spectroscopy of heavy metals. Like if you do metal-organic complexes and you have heavy transition metal ion, it often stays away from singlet state, and one needs nomenclature and understanding what is going on when these different sources of angular momentum add together. So basically we will deal for like 3-4 meetings with adding together angular momentum. So it is needed when one has an electron revolving around ion and it has its own momentum, and one needs to add them together and see what the total angular momentum of the system. Or there are several electrons, and it is not a big cornerstone of everything. It is rather narrow area for atomic spectroscopy and spectroscopy of metal impurities, but it is an important part for have the complete overview of the whole quantum theory. The approach to addition of angular momentum is less theoretical, less we will have less derivations compared to what we did before. It is more phenomenological because the basic ideas are relatively simple, but the solutions are long and hard to perceive by human mind. So we will just at the preliminary step we will learn how to read the solution and operate them, and then if you have time and steam we will go over how to get to the solutions or some logic behind how to get them. Okay. So what is angular momentum?
Momentum that moves around in a circle, or something that has momentum and is traveling in a circle. Or circular.
Not bad. Any other ideas?
Momentum due to spinning about some center of mass.
Arcos.
It's the answer of a professional physicist. So
yes.
Isn't it due to spinning inertia, thinking with inertia?
Yeah, all is correct. So quantitative measure of rotational motion. Something like more general. Like if something is spinning and you want to measure how quick it spins or what is the direction of the spinning, then we will have it. So anything that rotates has momentum. Where do we have the addition of angular momentum in the everyday life?
Addition?
Addition, yes. Any examples? I have forgotten to bring,
Like
but
if like a car going, if like a car on a track that goes around like this, you have to add the angular momentum of the wheels and the car going
Good.
around.
or if
A rocket ship flying off Earth, you have to add the rotation of the Earth plus its circular
good.
momentum around the sun.
That's horribly cool.
Oh, I'm sorry.
Well, if you have mechanical watches and you start rotating yourself, then you have.
Oh, yes.
Or if kid with a globe sits on a carousel.
Yeah.
I have a better example that I wanted to bring, but maybe I'll bring another time.
Bicycle wheel?
And if you go in circles.
Or you said Coriolis effect, that's like the water spinning in the drain, right?
Or if you have a sphere spinning and then it's taking off the sphere, you're not taking off from the equator. You have to stuff.
Did
Not just-
any of you play the RC drones?
Battery.
The quadrocopters? So they have several propellers, and it is stabilized in the air because they are counter-rotating in different directions. And there is one of the buttons that stops this balance of it doesn't rotate as a single unit because total angular momentum is 0. But if you get a little bit off, then it starts rotating as a whole. So the whole system gets a total angular momentum because of addition from these individual propellers. Okay, so there is a way to go from quantum description of individual rotating object 1, individual rotating object 2, to the measure of rotational motion in a quantum sense of the bigger system composed of two subsystems. And it is well-developed mathematical procedure in the most elegant way based on the creation and annihilation operators, same as we had in the Quantum 1 course for harmonic oscillator. There is an analog of raising and lowering operators for rotation. But this will be too long, especially with time limitation. So I suggest we'll meet today and overview the solution and the way to record and read the solution of this problem. And then, if you have steam and time, we'll go a little bit more into details. So, the solution of this problem was developed a long time before quantum theory was developed.
We share.
Good.
Oh.
I never thought you have so high standards.
I didn't want to, but
Okay, we shared. There you go.
you can have the one that we're not using at the moment. The little tray.
So those are German mathematicians who were dealing with rotation and continuous groups like 50 years before quantum theory was designed. But then later one has found that one can utilize their findings in the quantum theory related to rotation. So there is a very little homework that can be done in 3 minutes. No.
If I'm assuming it's like spin up times and one operator, just have 1, 0, and the matrix of like zeros and 1, 1, and you can go from alpha to beta.
So right now you are thinking as a theorist.
Oh.
In the next 20 minutes and during the weekend, we will think more like I don't know, teller accountants who just follow the prescriptions or whatever. A person who doesn't think but follows the rules, and the rules are very simple after we get used to them. So it will be not derivations but reading and writing the answer. So here is the key to this homework.
Oh, okay. That looks confusing.
And in the remaining time before we depart, we will just learn what this collection of numbers are. Okay, so I'm going to go to the blackboard and I will try to entertain you with explaining what it is and how to apply this table to this homework. And I will do something similar as a demonstration. Good. So we went through motivation, then we will go for eigenstate equation for rotating objects, and then we will just declare solution, discuss the indices. So the indices. The main challenge in this little chapter is that solution has too many indices, and one just needs to be very careful to operate them. So there is no mathematical challenge. It is just challenge for concentration and having enough coffee in your blood to keep track of object with 6 indices. If you can do it, then it's super easy. Indices, then CG for Clebsch-Gordan table, and an example. Declare solution, and here I will do example of triplet out of 2 spins. Out of 2 spins. So everything in quantum theory can be done, well, not everything, but many things can be done with time-independent Schrödinger equation. So one finds quantum state of a system if one selects correct arguments of the wave function, selects the Hamiltonian, and find eigenstates of this Hamiltonian. In addition, one can simplify the problem by finding of eigenstates of other operators that commute with Hamiltonian. And for if you have only rotation, other interactions are negligible, then instead of finding eigenstates of Hamiltonian, one can find eigenstates of total spin and z projection of a spin. System number 1. So we have spin 1 square wave function 1 is 1 square. And at the same time, the same eigenstates will be, yes, will match the eigenvalue equation for z projection of a spin of system 1. So one can write the same set of equations for system number 2, and the variables, the independent variables for system 1 and system 2 do not overlap. They are completely independent systems. There is no pumping of energy or whatever from one to another. We just look on them, later we will look on them as a unified system, but they do not have physical interactions. We just change the system of coordinates later. So total spin square for system 2 spin system 2 z component to z. So when we merge these systems together and start looking at them, it will be very similar to what we did in computational chemistry. We were finding eigenstates of systems with many degrees of freedom as a product of states of systems with less degrees of freedom. So we want to look on the total as a product of system 1 and system 2. And since it is not always possible, we are going to make some summation and some coefficients in front. So right now we are not solving. We assume that someone will solve this for us. And for most of simple systems, it is possible. So if we do have eigenstates of the bigger system, if the individual components do not interact, then one can write that total spin is summation S1 plus S2, and z components of the also can be added together. So this sets a basis for vector model of atom, of addition of angular momentum that we can draw when we meet next time. One makes vector summation of the angular momentum for system 1 and for system 2, and then gets the angular momentum for the combined system. And then for these operators, we do have S total square phi eigenvalue vector and z projection of the total spin so to match notations with between different textbooks, we can use the letter m instead of s sub z for magnetic quantum number, because it is the same. 2. So right now we are superficially skimming through these solutions, and we are not looking onto spherical functions. We do not look how they actually move. We just know that there are 3 sets of solutions, and each of solution is indicated, is labeled by 2 indices. So this solution for combined system is labeled by total spin and this projection on z-axis, magnetic quantum number. For system 1, it is S1 index and M1 index. And here it is S2 index and M2 index. So the problem that we are not going to solve, the solutions are already distributed. You have solutions for most simple systems in the table. Is the question, if we do have non-interacting systems with angular momentum, we know their eigenstates, there and there. And then after combining these 2 systems together, we also found their eigenstates. Can we expand eigenstate of the combined system in the basis of eigenstates of the lower level systems? And if we can, what will be the expansion coefficients? So you see, there are 2 indices, 2 indices, 2 indices. And coefficients show how to expand states labeled by these 2 indices over these states that are totally labeled by 4 indices, right? So this expansion coefficient, we have total 6 indices. Total spin, magnetic spin for the total system. Total spin system 1, magnetic quantum number for system 1. Total spin for system 2, magnetic number for system 2. And since we cannot change the total spin of the basis systems, we are not making summation over them. Those S1 and S2s are fixed, so summation goes only over M1 and M2. And in the summation, because of the conservation laws, M equals M1 plus M2. Any objections to the general idea? No. Okay. Too much. So I have about 5 minutes before you leave.
Yeah, you can keep going too, because
Thank you.
thanks for looking at my mind.
Here's our second board. So simplest example when we can practice, when this theory can be useful. When we have 2 independent spin 1/2 and then we merge them together. For example, helium atom or H2, where there are 2 electrons, and then we can take different orientations. So there is a basic knowledge that out of possible orientations of 2 spins, one can get 4 solutions. 1 solution corresponding to singlet, and 3 solutions corresponding to triplet, right? And it will deal with these quantum numbers. So, example, 2 spins 1/2. So solution number 1, when total spin will be 0 and projection for total m equals 0. This will be what we call single. And then this m equals s equals 0, m equals 0 state will be system 1, total spin equals 1/2, magnetic projection 1 equals 1/2, spin system 2 spin 1/2, projection minus 1/2, minus 1 square root of 2, S1 equals 1/2, M1 equals minus 1/2, S2 equals 1/2, M2 equals plus 1/2. It is a little long because some of you were dealing with singlets and triplets for a long time and you can intuitively understand them without this exhausting notation. But if we are going to like D elements or F elements with big angular momentum and several electrons, then this careful, meticulous notation can be helpful. So, solution number 2. So, for the triplet, there are 3 solutions: both up, both down, and superposition of up, down, and down, up. So triplet means total spin equals 1. And let's consider the solution with m equal 0. So no magnetic momentum, but total angular momentum is 1. So S equals 1, m equals 0. And then we basically repeat the same notation with the only difference in the sign here. 1 square root of 2. And with time, we can skip S1 equals and just write the number. 1/2, 1/2, 1/2, minus 1/2, plus 1 square root of 2, 1/2, minus 1/2, 1/2, plus 1. First spin, second spin, first spin, second spin. And those are solutions that we assume that we have found by some other methods. Now, how do we record? So these expansion coefficients are our goal. We need a nomenclature. We need a way to store these numbers to have an agreement how we store them, and then a way to read them. Okay? So we are going to build a table. Right now it will be very, very small table. So the table will consist of the 4 components. The actual cells of the table. And for this example of triplet with 0 magnetic projection, the content will be these Clebsch-Gordan coefficients. But now we need to fill the rows and column indices with the values of the angular momentum quantum numbers in such a way that we will agree and work with it with confidence. So we have rows, indices, and we have column. indices. And also we have a title of the table. So for the title, we will mention values of total spin of our basis, of our independent lower level systems. So S1 equals 1/2, S2 equals 1/2. So it will not change. Whatever we go for different coefficients, S1 and S2 are fixed for several solutions. Now, for the column, we will index our big system composed quantum numbers of the combined system. This equals 1, m equals 0. Okay? So we are done with this part, and we are done with values of the total spin for systems 1 and 2. And in the indices of the rows, we need to mention the magnetic quantum numbers that are used here. Right? M1 equals plus 1/2, M2 equals minus 1/2. So we do have our first record. So if we are looking for addition of 2 spin 1/2 momentum, and we want to see how they combine into quantum state with total spin 1 and magnetic projection 0, there will be a term including quantum state of first spin with magnetic projection plus 1/2 and second spin with magnetic projection minus 1/2, with coefficient in front equals square root of 1 over square root of 2. So this record in table corresponds to the first term. The second one, 1 equals minus 1/2, and 2 equals plus 1. And the expansion coefficient will be 1 over square root of 2. Okay? Now, if we do want to build the same table for singlet, we will just copy paste what we have here and plug in 1 minus, right? By analogy with this recording. So was it a question? So if we are looking onto the
What was 1/2 on the bottom?
yes. For singlet, it is minus. For triplet, they are plus. Wait. Here plus minus, here minus plus. If you mean about this.
Yeah, where does the minus come from?
It's over there.
So, in order to get this quantum state of the total combined system, we are adding together 2 terms. Each of the terms is the product of quantum states of spin 1 and spin 2 system, of system 1 and system 2. Okay? So for system 1 and for system 2, the total momentum is 1/2. This is total. Total and total. But the magnetic projection for system 1 is up, for system 2 is down.
Okay.
Okay?
Yeah, sorry.
And for the second term, it is opposite.
Yeah.
System 1 down, system 2 up.
So this table is only for this. It's S equals okay. So it's not for the singlet.
No, it is for triplet.
For triplet. Yeah.
So what I have written here is in a shorthand notation. So total spin 1, triplet, projection, magnetic projection 0, and here is the summation of two terms. Okay? So we are not first on the globe who were solving these problems and scrolling through the solutions, right? And this table is built in the same manner as we did here. So you have a little title that are used here, the table. Like what we did right now corresponds to left upper half. So we have title 1/2, 1/2. And right now we were corresponding to the state 1, 0, right? So you do see 3 tables enclosed into each other. All of these tables have L shape. We skip the first one and go to the first record in the second one. You see on the upper right there is 1, 0, right? And it has this 1/2, 1/2 in the cells, and plus 1/2, minus 1/2 on the rows indices. So the designers of this table intentionally skipped the square root symbol in order to make the table more common. But basically, if we have forgotten how to compose triplet out of 2 spins, you can look on this table and reconstruct this bra and cat notation out of the table. Okay? So let's probably finish about now. And at the weekend, do not spend more than 5 minutes. If it doesn't work, we'll discuss it in the class. Try to look on the third, on the right side, angular momentum 2 and angular momentum 1, and expand quantum state with total spin 2 and magnetic projection plus 1 in the basis of the states. Just build this bra and cat notation out of the table. There are no limitations. If you can consult with friends, colleagues, internet, it is fine. It's not for grading, it's more for learning and getting the logic. And after we get this idea, we'll try to go a little bit more into details where these coefficients are coming from. But going into boring mathematical details right away would kill the interest, at least in me.
So we're looking at this, if someone gives us a table, then we're constructing.
Yes, table is given. One of my acquaintances was teaching at middle school and giving a quiz to these little kids. And quiz is distributed. Kids are sitting and solving something, and one of them is sitting and doing nothing. So the friend is coming and asking like, why are you not solving the problem? I don't know. In the beginning of the problem, there is a prerequisite. You are given an ice cube. with the density and size and all that. So what? But I do not have ice cube. I'm waiting until you distribute it to me. But here you do have a table. In this, declaration at the first line of the homework should be, you are provided a table of Clebsch-Gordan coefficients. So this camera shows you. This camera shows me. The meeting is over.